All right, well, we've talked about the absolute approach to finding velocity and acceleration of complicated mechanisms. We're now going to talk about the relative equation for velocity. We've used the relative velocity equation several times. We used it in Chapter 12 when we were trying finding velocity of A with respect to B. We used it in impact, we used it in the conservation of momentum, and we used it in two-dimensional conservation of momentum in Chapter 15. So we're familiar with the form of the equation and the use of V of A is equal, or V of B is equal to V of A plus the velocity of B with respect to A. We know that the actual velocity is the vector sum of components. And the vector sum could be i's and j's, or x's and y's, or it could be the velocity of A plus the velocity of B with respect to A is equal to the velocity of B, which is the equation. All right, if an object is rotating about a fixed axis, the relative equation applies to that. So let's see that we have this bar rotating about A. It's got an omega, it's got an r. We know that the velocity of B is always tangent to the path and perpendicular to the line connecting the two points. So we see the velocity of B is going in that direction, and we can write the equation, the velocity of B is equal to the velocity of A plus the velocity of B with respect to A, where the velocity of B with respect to A is equal to r omega. Well, if A is not moving, then the velocity of A is equal to 0. So we can interpret the relative term as the velocity of B as if A wasn't moving at all. All right, we'll use that term more than over and over, and I think you'll be familiar with it. So if an object is translating, however, there is no rotation. So let's say that this object is moving in that direction, but the relative equation still applies. We're just going to say that the velocity of B is equal to the velocity of A plus the velocity of B with respect to A, where V of B with respect to A is 0. In other words, it's not moving relative to A, so that says that V of B is equal to A. Well, the common occurrence, however, is where V of A is not equal to 0 and B rotates about A, such that the equation applies, and we are now looking at the vector sum of the two components. We're going to have a velocity of A, which applies to B because it's both translating and rotating. So when it's translating and rotating, the translating form component comes up to B, and the rotation component comes up to B, and the actual velocity of B is going to be the vector sum. All right, so here's just a very easy example. Let's just say that this bar is moving and rotating in this space, and we say that VA is equal to 3I. We're going to say that the length is 1 meter and that it has some omega of 2 radians per second. We're just going to put the equation together. We're going to say that the actual velocity of B is equal to 3I, which is velocity of A. And then the B with respect to A has I and J components, and we have to look kind of carefully. I just picked an angle here of 60 degrees, but we know that there's going to be some component in this direction as well as some component in that direction. And so those components are going to be the magnitude of this term of B with respect to A is the r omega, and then it's going to have some component in the x direction of cosine 30, component in the j direction of sine 30. We multiply all that out, and we can see that the actual velocity of B is going to be 4.732 I minus 0.5 j. All right, we would like to introduce into the relative equation now a new form for the with respect to term. And the with respect to term is an r omega term, but we're going to put this r omega as a cross product, and we're going to cross omega with a position vector. All right, so the new form now looks like V of B is equal to V of A, plus, instead of B with respect to A, we now have this omega cross R, or position of B with respect to A. Omega now is a vector. It's going to be in K space, will be in vertical space. The relative position, this term will be a vector in I and J space. Okay, recall from our work with absolute that in the absolute analysis, the lengths of the links could be changing, and we were concerned about the rotation actually of only one link, and all of our work we did in that, we were only concerned about the rotation of one piece of it. In the relative analysis, the lengths of the links must be fixed, but however more than one of them may have rotation. So there is some little difference in how we would approach the problem, or which approach we would use to solve a problem. One might be a little bit easier than the other one. All right, so back to the relative equation. We know that with respect to a term is a cross product, and so we're going to take this cross product in two dimensions. And we're going to say that k cross I is j, and k cross j is negative I. Recall from your work in statics, the cross product, and maybe calculus, the cross product is a 3-dimension, or a 3x3 matrix, determinant of a 3x3 matrix. So it's pretty simple to do, but it's even easier to do it when we're only concerned about 2 dimensions. And so these are the signs that we'll be cognizant of. And recall also that omega being in the k space, omega will be by the right-hand rule. We're going to say positive is counterclockwise and negative is clockwise. Okay, so now back to our little problem. We can do this again using the relative, this other term for in the relative equation. And we're going to say that here's our bar that's both moving and rotating. And we can say that the velocity of A is still the same. The velocity of B now, that's what we're looking for, our unknown, is going to be equal to the velocity of A plus omega cross R, or position of B with respect to A. All right, so we had a 60-degree angle. We have some omega. We called that omega 2 radians per second. And we had this length here of 1 meter. So let's just fill in the gaps and see what we have. V of A is 3I. That's going in that direction. Omega, we've drawn it in this direction. And so that's clockwise, which would make that a negative k. So we bring negative k, the vector omega with a bar is now negative k with a hat. And we're going to cross that with the position of B with respect to A. So B is up here, A is down here, so B with respect to A is going to be over in this direction plus up in that direction. So it'll be a cosine component in the x, a sine component in the y, and I'll just put both of those terms in there. The length is 1 meter, and those are the directions. And the cross product now will say that k cross I is going to be a j. However, I have a negative term there. So that means that when I do the product, I'll have a negative 1 cosine 60 j. Then I cross it into this term. K cross j is negative I. However, I had a negative to start with, so 2 negatives make a positive, and that makes me 1 sine 60 omega in the I direction. Multiplying all that out, I get the same answer that we had before. V of B is equal to 4.732 I minus 0.5 j. Okay, with that, then let's solve a little more complicated problem. Here is a rotating bar that is going in this direction. It's tied with a pin here to this bar, which is hooked to this cylinder, or into this piston in this cylinder, rolling up and down there. And we can tell which way things are going. We know that this piston is constrained to move in this direction only. We know that VB is going to be going in this direction. So we can write in our what we know about the velocity of B, since it is an r omega. We know that it's a circular motion around this point. We know that the velocity of B is only going to be in this direction. So I can say VB is going right like that. And it also has some components, because we're going to have to analyze those things. We know that it's going to have a component in the x direction and a component in the y direction. And looking at this angle, if that's angle 30, then this is angle 30, which means that this is going to be 60 on the inside there, which makes that the velocity of B and I and j, we can say that that's going to have a minus cosine 60 in the x direction, or I direction, and a positive sine 60 in the y direction, or j direction. So I'll just write that down. VB is going to be r omega, that's the magnitude, which is 0.3 times 6 radians per second. And then the direction is going to be minus cosine 60 in the I, plus sine 60 in the j, and I can multiply that out. All right, how about the velocity of C? Velocity of C, we know it's constrained to move in this slot, so I'm just going to draw it up like that. Velocity of C. And because we need to know its I and j components, I'll say that it has an I component that way and a j component that way. This is 60, so that's 60. And so I can write the velocity of c like this. I know that it's a vector. I don't know the magnitude. That's actually what we're looking for. We're looking for the magnitude of VC. So we know that it has a cosine 60 in the I direction and a sine 60 in the j direction. Now, the with respect to term is a position vector, and we're going to say that r, the position of c with respect to b, here's c, and with respect to b. So if I'm standing on b where c is, I'm only going in that direction, so it'll be plus 5 or plus 0.5 in the I direction, so that's all that is. Okay, now let's write the whole equation out. Velocity of c is the velocity of b plus omega cross r of c with respect to b. So I've got my terms for VC, put those down there. Got my terms for VB, put those in my equation there. Now let's do our cross product. I'm going to say that, or I'm going to put our terms in for the cross product. So omega, I didn't draw omega yet. So let's assume omega is going in that direction. We'll say an omega BC. Okay, so I drew it going in the positive direction, in a counterclockwise direction. So I'll say that k omega cross the position vector of 0.5i. So k omega cross 0.5i. All right, let's do the cross product. I'll bring those terms down. I multiplied that out. And the cross product here is going to k cross I is j. That's positive j. And there aren't any other terms there, so I'll just say that that is going to be 0.5 omega j. All right, 0.5 omega j in that cross product. Now I can combine my i's and j's. I got an I term on this side, so I'm going to say VC of cosine 60 is an I term. Nothing there. E is equal to negative 0.9. That's an I term. Those are both j terms. So I can evaluate this term directly. I can see that VC is now a negative 1.8. Negative 1.8. I drew it going up the hill like that. I solved for it being a negative number, which means that it is actually going in that direction. Now I'm okay with leaving it as a negative number as long as it agrees with my sign. I'll leave my sign, or I'll leave my arrow. As long as my sign and my arrow match. I'll leave my arrow that way, and I leave the sign SIGN of that, meaning it's a negative number, so I know that it's going the other direction. How about the J's? Let's talk about the J's. We've got VC sine 60 in my J. I've got 1.559 plus 0.5 omega. I have VC already solved for. I can solve for omega. And omega is now negative 6.235 radians per second. Now this is omega of the length BC. It's a negative number. So let's go back and look at the drawing. If it's a negative number, I drew it in this direction. It means it is actually going in the other direction. That's omega actual. And it is actually going at 6.4 or 6.24 radians per second going in the other direction. But again, as long as the arrow on my drawing and the magnitude that I solve for, as long as there's a negative number, I know that I just drew my arrow incorrectly, and there's no real reason to go back and do all the math or redo all the math.